Hey, I guess you've started to realise what we're doing here. We're trying to look at all aspects of geometry in terms of vectors. And what's left now? Well, you could have probably guessed from our 2D presentation in the prequel to this particular course that it's finding the equation of a line in space now. Not in 2 dimensions, but in 3D space. So here's a question for you here. Right now, what were we going to say? What would the equation of a line in 3D look like? Okay, so we're going to investigate the few little pictures around the screen here. Oh, this looks like projection or something here. Oh, parallel lines, better see what they produce. We've already looked at the cross product, so you might have an idea there, and finding intersections and angles. I think we can do that already. Something to do with the dot product, isn't it? Think so. And this is something to look forward to. What's going on here? Lots of stuff there. But you'll amaze yourself in this presentation, where you'll get to be quite competent with working with lines in space and starting to really see the 3D nature of space, if you like. Okay, well, let's go down now and start with this question. Well, we haven't got a question first. First of all, it's got a screen clipping here from Hayes and Harris Publications, so it'd be good to grab their book and have a look there as well. A line in space, and this is the same for 2D now, is a straight line which continues indefinitely in both directions and contains a continuous infinite set of points. Continuous, no breaks in it, therefore. Okay, and what I'd like to just mention now, going back to the idea of ratio of division, just keep in mind when we say the line AB, we mean really the line segment. And this is covered by this definition here. It's an infinite set of points that continues in both directions. So it's not just a line segment. As we found with external division, P could divide the line AB, okay, from an external point, because P is on that a continuous line AB with an infinite set of points. So our equation's got to accommodate these 2 directions and the idea of an infinite set of points. So think about that. Okay, let's go down now, and now I'm going to ask you the question that I meant to say before. Red hot burning question here, mate. What does the equation of a line mean anyway? What does it mean? Now, we've had this for a few years now. The equation of something, the equation of a line, the equation of a curve, parametric equations you might have seen. Oh, lots of stuff. So let's have a look. Let's try to get our head around the idea of an equation. So perhaps we'd see something simple as a rule, which all points must obey to lie on that shape. All points, hang on, I'll just get rid of this here. All points must obey to lie on, in this case, the line. And we would extend that to any particular shape. Okay, that's what we mean by an equation, which all points must obey. So the points here have coordinates x, y, and z. And what we want to do is to say, what's the relationship between x, y, and z? That special relationship, so that all the points will line up. That's what we're trying to do. So we need an equation or a rule connecting x, y, and z. Fairly simple idea. And here it is here. We might say, well, we're going to fix a point. So here we're going to fix point F, and we're going to give it a direction vector. And we're going to say, what's the rule for this point? Any general points, our point here with x, y, and z in it, might be called our general point. We've got to describe what that general point must look like if it's to lie on the line through this point and in the direction of u. So we're fixing a line in space and then describing the rule for the general point. Do you get it? Hope you do, because you've been doing this in 2D stuff, but not vectors, but in coordinate geometry for some years now. So try and get your head around that one. All right, let's go down and see what we can do with it. And here we are. Here's some from Hayes and Harris. And I've left this one blank over here because I want to give you an alternative way of generating the equation of a line, the vector equation of a line. So just as I said before, here's our problem. So we're supposing mx, y, z is a point free to move, okay? So it's a general point. It could be there, it could be up here, it could be further down here, all on that line in either direction. And we're saying the direction that we're specifying for the line is given by the u vector ABC. So what could you say about Fm? Here's the starting point. We're going to try to work this point into our vectors because it's the point that we need to describe the position of, our general point. So it's t times u, isn't it? So Fm, that vector there from F to M, has to be some scalar multiple of u. So we're picking up the idea of incorporating this point and this direction. And the scalar t would be what? We'll think about this later because we're going to come across parametric equations again. And parametric equations involve a parameter. Well, we might like to look at what the meaning of this particular parameter is. All right, so what could we say? Well, Fm is this, isn't it? It's x take the x coordinate of that, y, and we're saying now, just keep in mind, we know f. We know the coordinates of f because we've got to fix our line in space and then give it a direction. So we know that. So it's t times our direction vector is a vector equation. So therefore we can say x take x1 is t by a, y take y1 is t by b, and t by c. Here we are. So there is a set of parametric equations to describe what x must be, what y must be, and what z must be for that general point x, y, z to lie on that line. So you can see we're fixing it through our point F and we're giving it the direction A, B, C and T, lots of that. So what's it saying? Well, if you change T, you change M. So we can change T. If we made T greater than naught, it would go in one direction. T less than naught, go in the opposite direction. And K could be any real number. T could be any real number here. Okay, so you could have little short spurts away from F or longer ones. You get the idea. Well, I'm going to do it another way now, and I like this way a little bit better because of, well, you'll see, I think. Okay, let's imagine we have the origin somewhere on the 3D plane, or sorry, in 3D space. We've got a set of axes, so we have the origin. Now our aim here is to travel out to a point on this particular line, defined by this point and this direction vector. So let's make up a direction vector, a position vector for this point, OM. Okay, OM would be x, y, z. So you can see we're cutting directly to the chase with this method. We're saying, hey, how do you get out there? Let's find the equation for that point, general point M on the line. Well, how do you get to M? Well, I could travel this way. I could go OF, so this is also equal to OF, and plus what? Well, I've got to travel down here a certain scalar multiple of u. Okay, so let's make those all into vectors now. So x, y, z equals OF, which is x1, which is known, y1, z1, plus t times u. I like this one a little bit better. Okay, so, and what is u? It's A, B, C. I think we're saying we're letting it be t by our vector A, B, C. So we come directly to this vector equation, and you can unpack it in the same way. X equals x1 plus t times a, here it is, those components make up the overall x component. Y equals y1 plus t times b, and z equals z1 plus t times c. Okay, which way do you like? You come to the same point down here at the end with the parametric equations, but I like going straight, I suppose, to this line with the idea that we're specifying how to get to M, a general point on the line, from O with a position vector, which is a known vector travelling to a known point, and t times the direction vector. All right, I hope that's not too complicated for you. You might have to look back through that. Get the idea. Remember, vectors are displacements in the plane. That helps you understand all our proofs and our work. Displacements in the plane. We are moving a point. Okay. All right. So let's go on and have a look. So here we are. Hayes and Harris have this definition now. So there's the one that you do from the FM approach, and here's the one with the position vector of the general point. You travel out to it by travelling out to a known point on the line, and then a scalar multiple of the direction vector. Okay, and then the parametric equations are these, splitting it down into how do you get x, y and z separately. Now, here's an interesting one here. How do you relate it back to the Cartesian set of axes there, the x, y, z axes, if you like, call it the Cartesian form? You're trying to relate x, y and z directly with each other without a t. So the way in which we do that is to take this and say x, take x1 on A would equal t, and that would also equal, take this one here, rearrange it, y, take y1 on B, and take t from here, because t is the same, isn't it, in each of the vector forms there, Cartesian equations. T is the same. T is a member of R and is constant for this particular situation. That is, you move a certain amount, and that can vary, but that's going to be the same movement in terms of the components. Scalar multiple of each of them is going to be the same. And about now, I think you should be saying t is a parameter. Okay, so what is the property of the system that it is representing? Remember, a parameter is another property of the system. We've got x, y, z's all over the place there, and that's the basic definition of our 3D system. But we're bringing in another parameter, relating the x, y, z-ness to t, or directly, but this has been untidy, isn't it? The Cartesian form here, the two equal signs in there. So it's very hard to have a Cartesian form relating x, y and z. So we go to parametric form, but what on earth is this property of the system that we're relating x, y and z to here? Can you think of it? Just pause it for a bit. What is t representing here? Okay. Well, just think, t is the scalar multiple of the direction vector. Okay, of the direction vector. So what that property of the system is, so it's equivalent to saying how many lots of the direction vector do you need to get to the point? Okay. Do you need? So you're defining your point here. So come back up to this asterisk up here. You're defining your general point on the line x, y, z in terms of how far you've got to travel along the direction vector A, B, C to get to your point. So here you are. There's your definition of that property of the system. How many lots of the direction vector do you need to get to any point? It could be positive, it could be negative. You could go up the line or down the line if you like, along the line in both directions. Do you get it? I want you to get up close and personal with this. Remember the hierarchy, Huddy's hierarchy. You can learn the rules. Here's all the rules, mate. What's the concept? What's really going on there? What's the idea? And then I see it. So we can get the idea of this growth factor, if you like. Oh, there's a Huddyism. T is a growth factor. Hey, I'm going to come back to that later. T is the growth factor of the line. That's not good maths. Well, it's a way of thinking, and that's what I want you to do. It's a growth factor. You can get the idea that you have to have scalar multiples. But can you get the idea that t makes the line grow in both directions, and that it is a parameter which is representing how many lots of t you have to get to that next point? All right, and every point is going to have a different t. Okay, I hope you're getting that. Okay, come down. Let's have a look at doing some problems with it now. Find the vector equation, parametric equations, and the Cartesian equations of the line through this point in the direction of that one. So we'll move out to the point. Okay, so x, y, z, first of all, we'll move out to that point from O. So that's the position vector of that point. So it's got vector symbols here. And then we're going to travel along the line t lots of the direction vector. Just remember here, this is equivalent to component form 4, 5, and -6. Okay, and t is a member of R. Okay, so parametric equations, let's put x is that 1 plus 4t. Okay, y is -2 plus 5t. Okay, and z is 3 take 6t. Okay, so the Cartesian equations are rearranging each of these for t's. So let's do this one over here. So x take 1 on 4 equals t. And here y plus 2 on 5 equals t. Just rearranging them. Z take 3 on -6 equals t. So they become the Cartesian equations. Just notice, we want to go back and forth between all these, so just notice what happens here. These numbers down here are the components of the direction vector, aren't they? 4, 5, and -6, if we keep it in that simple form. So just watch the movement of the coefficients here and the constants in these relationships. And remember where it comes from. I really do think that the simplest way of looking at this is to think of x, y, z as travel out from O to the general point, wherever that might be, and that's equal to travel out to a given point from O, so that's this sort of thing, and then move along back to that general point by t lots of the direction vector. Okay, I think it's a simple way of thinking. Okay, have a go, and here we are down here with these. So I want you to pause the presentation, have a go. As usual, the fully worked solutions are just down below here, so I'll show you those in a minute. Okay, here we go. Let's have a look at them. Question 1 and 2. Just check the ideas there. Okay. And question 3. All right, how are you going? You want to be pretty familiar with this stuff because this is crucial in our journey in having vector geometry in 3D space now. All right, let's do some more and see what you think. Okay, we've done the basic idea of the vector equation now, so we can play around with it a bit and go forwards and backwards. So now they're going to ask you to go backwards. Here's the Cartesian form for the equation of a line in 3D. So I guess we've already answered the question, what does the equation of a line in 3D look like? Well, it looks like three things, doesn't it? A vector equation, parametric equations, or a Cartesian equation. So write down the parametric equation of the line. So we've got to unpack this. Write down the vector equation and find the point on the line with z coordinate 5. Okay, just remember with the Cartesian form, put them equal to t. And so here we will say x take, they've left this out, x take 2 equals t. So x equals t plus 2 or 2 plus t. Then we'll take 1 take y on 2 equals t. So 1 take y equals 2t. Or y equals 1 plus 2t. Now you've got to rearrange that there. Sorry, 1 take 2t. 1 take 2t here. I'm doing it in my head, just want to watch that. And so here z plus 3 on neg 1 equals t. So z equals neg t take 3. Or we usually put the number in front, neg 3 take t. Okay, so that's how you unpack those. You don't forget to put that and that make up these three little expressions. So therefore we've got the parametric equations now. And the convention is to put these first, okay, the numbers first, because we're going to remember now that t here is going to be the parameter, and that's going to be the number of lots of the component of the direction vector. So what is the direction vector? It's 1t, neg 2t, and neg 1. So here the coefficients of t are the direction vector of the line. Okay, so I said you'd have to go backwards. Just remember the line is defined by this, and this is the known point, and t times the direction vector. So where do the components of the direction vector end up? They are over here, coefficients of t. So the numbers in front of t have come originally, just remember the origins of this, from t lots of the direction vector. So they are the components of the direction vector. Now, find the point on the line with z coordinate 5. Okay, so we could use that, and I wouldn't go back to here. We've got the parametric equations, so say z equals neg 3 take t, and we want that to equal 5. So that defines our neg t, that defines our t value. So specifying one of those coordinates or components of the direction vector, or coordinates of the particular point we're looking at, gives us a t, and that locks us in, doesn't it? Locking us in. Once you specify a t, you lock in the point on the line. Don't you? Because you're saying exactly how far along the line from the given point over here, the given vector there, you're going to then go. And once you say t is a value, then you're locking in a point. Okay, because fix that, and you've got x, y, and z fixed, x, y, and z equals this. Okay, so think of that. As soon as you specify a value of t, you're locking down the line. You've stopped the growth of the line because t allows it to grow. Okay, that's a way of thinking. Not a way of writing it mathematically, however. It's a Huddyism. Okay, so here we go. You will now sub t as neg 8 into each of them. Again, I prefer this line here. The parametric equation's easier to find the coordinates there. Okay, so here, that's what they're doing down here. So the point is neg 6, 17, 5. Okay, we've travelled out to that point and then gone along the line. We've travelled out to, the fixed point there, and then travelled along from z equals 5 point, t equals neg 8 to get our to z equals 5. Okay, let's have a look at doing some. You need to keep the practicing up here to make sure you understand what's going on. So here we are, 4 and 5, backwards and forwards to find the various equations of the line. Just notice here they want the vector form, not the direction vector alone, but the vector form. Okay, so remember now the line in 3D, what does it look like? It has three forms. The vector equation, let's just summarise this here, which is up through a known point, call it x1, y1, z1, going out to that point, plus t lots of the direction vector. So that is a vector equation. Then we have the parametrics, breaking those down now. Y equals y1 plus t times b, and z equals z1 plus t times c. And then we have the Cartesian form, x take x1 on a, equals y take y1 on B equals z take z1 on C. And they're all equal to 2. We don't write that in. So the equation of a line in 3D takes three forms, and you should be able to work backwards and forwards through those. So that's what these questions here are about. All right, pause the presentation and have a go. I'll show you the solutions down below. Okay, let's look at the solutions now. Okay, 4 and 5, and just make sure you're understanding those now. Okay, let's go on. We've got a few exciting pieces to do now that we've established the idea of those equations there. So here, find the parametric equations, coordinates of the point where the line with parametric equations that meets the x, o, y plane and so on. Just have to be a little bit tricky-dicky here because, I'll give you a hint, on the x, o, z plane, of course, y will be 0. Okay, let's just check that. The x, o, z plane, x, y and z. The x, o, z plane here. Okay, the x, o, z plane has y equals 0. So it's specifying one of the coordinates, and therefore we can specify t. Okay, so find points on the line with parametric equations, these, which are 5√3 units from the point 1, 0, neg 2. So to do that, you'll consider the point on here as 2 take t, 3 plus 2t, and 1 plus t. Okay, and work between that point and this to get that distance, and that'll give you the t value. Okay, so you get that idea now. There could be a couple of answers to that one. Okay, 5√3 units here on a line, 5√3 units from this point on this line. So it could be a couple of different spots there. Consider the pair of lines that, write down A and B, the direction vectors of the line, find the parametric equations, okay? So have a look at those and see what you think. And I'm going to show you the answers now. Okay, so there's 6 and part of 7. Okay, I think probably 7 is the more challenging one here. There's 7 part of 8. Okay, and there's 8. And then 9. All right, let's go on now and have a look at example 30 here. So find the coordinates of the foot of the perpendicular from P to the line with parametric equations that. Okay, let's have a look now at that and see what we've got there. So we'll just pause it here for a minute. Okay, so here we are back again. What we're going to do here is to find the coordinates of the foot of the perpendicular from P to the line with those parametric equations. So we need to draw a sketch here. Here's the point, and we want it to be perpendicular to this line given by V, or the parametric equations, the direction V, and this is the set of parametric equations. So we want that to be 90 degrees. So one little trick here is to let A have the general parametric coordinates, if you like, given by that. Okay, so if that's any point on the line, then PA, our point from there to there, would be given by this vector. And there's the direction vector of the line. Okay, what is it? How do they get that? There's the direction of the line. So where we are, if we have this perpendicular, that's supposed to be perpendicular because we want this point here. So therefore the dot product must be 0. And when you do that, just look at the components, that one by that one, plus this one by this one, the dot product. Remember the dot product, A dot B is A1 B1 plus A2 B2 plus A3 B3. Okay, so then we can get an equation in T, and we find T is 1. So the point here on that line, it has T equals 1. And once you find the T value, that locks in a point. So we can substitute the T back in there and find that you get the point is 3 neg 1, 4. Now, we could also, therefore, find how far it was, that point A, by finding the length of PA, because we had PA back up here, and so we could put T is 1 in there and find PA, and the length of PA is root 26 units. Now, what do you get out of all that? Here is the important point up here. If you're trying to find a point on a line, use the parametric equations there to generalize that point. So you're going to call it the parametric x, y, and z. And then you're going to go and find t to find the specific point that's locked in by that t value. So a general point on a line is represented in this 3D work by the parametric equation. So x is that in general, y is that, and z is that. So this is very important now. In further work later on as well, if you're looking at doing finding a point which could be anywhere on the line, you let it have that parametric form, and then hunt for t to lock it in. All right, let's have a go at doing some. So here we are, 10 and 11. Okay, find the coordinates to the foot of the perpendicular. You will say the general point on the line is given by those coordinates. Okay, and then find t. Remember, t specifies a particular point. Once you do that, you stop the growth of the line. Okay, remember, you're travelling out to the line, and then you're moving along it. Perhaps you're saying t times the direction vector a to get to your point. Oops, your point here, x, y, z. So that's why t is the growth factor. If you stop it growing by specifying what t is, you arrive at a particular point. Okay, and you don't know what that point is, so you will let it be that. 1 plus t, 2 take t, 3 plus t. All right, get the idea. Have a go. I think here we're starting to get an idea. You could change the parameter there to s. If you're talking about two different equations within the one problem, two different lines, you'd use a different parameter. We'll come across that later on. So have a go at these two. And here are the solutions. There's 10. A, we'll come and finish off B in a minute. Okay, notice the idea that the point you're looking for has the general coordinates given by the parametric equations. Okay, let's go to B. Okay, so there's B. I think diagrams help quite a bit. Okay, 11, part A. And B. Okay, here we are. Well, we're building up. How would you find the shortest distance from a point to a line? So here we have an idea. We have a line, and we're trying to work out the distance of point P to the line. So that's this distance here. The shortest distance is the perpendicular distance. So get a picture here. Now, what are we going to do this? Well, if we know a point on the line, let's construct a vector AP. Okay, now AP, we did this before, where we wanted to find this distance here. And that was the projection. Do you remember that? And that was this vector AP dot V divided by the length of V. I hope you remember that derivation. A dot product, you get that. Well, this is going to be pretty similar because we want D, and you can say here that D over the length of AP is the sine of that theta there, isn't it? If the theta, the angle between that AP vector and the given line that we're looking at is theta, then you could say this. And from that, of course, we get the idea that it's AP cross V divided by the length of V. So that gives us this distance here. So you take AP cross V divided by length of V. I wonder if you can see it from here. We're going to prove it now. Okay, so come down and let's have a look at what the proof looks like. I just did it for you basically there. So here, that D, here it is, here's the crucial thing, D over the length of AP, a little bit of SOHCAHTOA in this triangle here, basic trigonometry. Okay, and so D equals length of AP sine theta. But remember the cross product, like the dot product, length of one, length of the other, by this time the sine of theta compared to the dot product, the cos of theta. So we've got that, and if we divide by V, we'll get the piece that we want, length of AP sine theta. So we can have the cross product divided by the length of V will give us this distance D. So there we have it. Let's summarise this then. D is AP cross V, length of that, divided by the length of V. And this one here, we'll just rub this out. I want you to have this one. This is the projection. So that's AP dot V. This is the vector V, they've left that out, the direction of the line there. AP dot V divided by the length of V, or the length of those, because we want a positive distance there. So they're very similar. One is using what? Using the idea of the sine of theta, opposite, and this one's using the idea of cos of theta. So that's fairly easy to remember there, okay? And it comes down to the idea, of course, that the cross product, AP cross V, the size of that is the length of AP by the length of V by sine of theta. And the dot product, the length of that is the length of AP by length of V cos of theta. That's what we're using there. In fact, this one also, so we put here also, AP dot V equals the length of AP, length of V cos theta, if we're trying to actually find the angle cos theta, therefore. All right, well, let's have a look then. What we should have here, sorry. The size of all that has to be positive. All right, so do you get the idea here? Well, we're trying to do everything in 3D geometry with vectors, angles and lengths of lines and so on. So this is the distance of a point, shortest distance, perpendicular distance. Without the perpendicular, can't use sine and cos like that. Perpendicular distance of the point from the line. Okay, come down and let's have a look at some examples and get you to do some in a minute. We're travelling quite well here. So what we're going to do now is to use the distance formula to find the shortest distance from that point to the line there. Okay, so it's the same as the example we had a look in 30, same idea. So here we have the point P, and what we're going to do is say the direction of the vector of the line, the direction vector of the line is 2, 3, just remember it's 2, 3, 1, coefficients of t, because it was t times the direction vector. So here what we can say, if t equals 0, that we can generate a point on the line. Remember, it doesn't matter which point we use here. We want a point A. Then we'll travel out to P, wherever it is, and we'll do our thing here. Okay, so A can be any point. Okay, any point on the line. So let's sub t is 0 to get a simple point. So if you sub t is 0 back in here, you get 1, neg 4, 3. So we're going to then generate our vector AP. So it's from this point here to P. So it's neg 1, take 1, so neg 1, take 1, 2, take neg 4. Okay, there it is there. So it's going to give us negative by negative is a positive, and 3 take 3 is 0. Please note you can choose any t here to specify any point A on the line. Now you might ask why. Well, if A changes, AP cross V will change. Okay, and so here, and so all of those lengths will change in proportion, won't they? If A is a different point, then the vector V coming from there have a different length, and this will be still in the same ratio there. Okay, and so you'll still get the same distance, even if you choose a different point. Think about that one. Think about that one. Okay, so AP cross V, they've left out the I, J's and K's. Still, I think it's best to look at this as the determinant of 3 by 3 like that, so that you then do the whole thing carefully. But these are the cofactor matrices whose determinants you're going to use. So it becomes 6 to neg 18. So you need that cross product, and then dividing by the length of the vector 2, 3, 1. So it's that one divided by the length here. And so we want the length of the cross product, square root of the sum of the each component squared, and so on. So here, root 364 over root 14, or the root of 364 over 14, done on the calculator is root 26. Okay, so on the Casio, if you want it in that form, you keep it in math mode in setup and use run in math mode. Okay, all right, let's go and do some and see what you think. Check your answers to question 11 using the distance from a point to a line formula. Okay, but think about the formula when you're using it. Don't just copy it in monkey fashion. Monkeys copy each other. Think about it. So here, this is the equation of a sphere. Oh, we haven't had that before. Centre 0, 0, 0, and radius root 26. Find the points where the line through that meets the given sphere. So line through that and that. Now that's a thinking question. It's meeting the sphere. So what do you want? You want a point on this line. Point on the line joining that. Oh, you have to hunt for a T. And if it's a point, how will you specify it? An unknown point on the sphere, you will use the parametric equations to specify the general point. Okay, think about it. I'll get you to pause it now and have a go, and I'll show you the answers. Here we go. Here are the answers here. For 12, I'll just come up a little bit, see if we can get it all on there. Yep, so 12. Okay, let's go on then to 13. Right, now these answers here you can give also 3 significant figures. In this course you can state the answer in exact form or to 3 significant figures unless otherwise stated. So that sort of, those sorts of conventions apply there. Okay, nearly finished. I suppose you're getting a bit tired there, but let's see what else we've got. Line classification. Well, this is fairly difficult in 3D land, isn't it? Because lines could completely miss each other in space. That's what they try and indicate here. See the gap in there? In other words, if you were to draw it in 3D land on 2D paper, that's not easy, mate. But here, you might have a line going there and one going underneath it, quite separated in space. Such lines are called skew. Okay, they miss each other completely. Okay, they could, however, be parallel or intersecting or miss each other completely. So there is what? An infinite number of possibilities here of skewness. So we don't try to show skewness, we do it by default. So skew lines are any lines which are neither parallel nor intersecting. So if they don't intersect, they're not parallel. They must miss each other in space completely, like that. So that's the idea. Okay. Now, if the lines are parallel, the angle between them is naught, so we're going to use that. If the lines are intersecting, the angle between them is theta, so this idea here. If the lines are skewed, there is still an angle that one line makes with the other if we translate one line down to intersect the other. Okay, so the angle between the original lines is defined as the angle between the intersecting lines. So that's interesting. So I might like my diagram better. So here we will say, how can there be an angle between these lines when one goes under the other? So the idea is we bring this down so that it intersects, and then it's that angle there. That's what we define. So they can have an angle between them, even though they're separated in space. Sounds difficult, doesn't it? But if you think about aeroplanes or something flying, they will have a bearing, won't they? This one might be heading off here. This one is heading off here. Now, they're not going to hit each other because they're in different planes, different directions as well. But we might want to compare the bearings. That's heading off east or something, and this is heading off maybe 20 degrees true or something. Okay, so there is still a relevance to an angle between two lines in space that don't intersect. Okay, you can think of it in a practical sense. Bearings are a 2D nature, but then you've got your 3D space on top of that, if you like. So here's a drawing down here. The idea of shifting one line so you look at the angle between them. All right, so you see the 3D nature of things makes it quite interesting, doesn't it? You could say more complicated, but I'd like to say interesting to say all the things that could possibly happen there. All right, so let's go down and have a look at using some of this stuff. So there's an equation, line 1 and line 2. Oh, now notice this. This is very, very important. You use a different parameter for the two lines here. Why? Because when you specify the growth of the line or getting a general point, this is how many multiples of the direction vector you need to get to the point. Now, no one says these should be the same in both lines. So if you're looking to show they're intersecting, you're looking to show that when you start on one at a particular fixed point and coming along, you want to know where it intersects there. And then on the other one, you start with a fixed point, you want to know. It would be almost impossible to start at a certain fixed point here and go t lots of its direction vector, and then start at a fixed point here and want to go exactly the same multiple of its direction vector to get to a common point. Well, you would hardly ever find a common point that way. So this point might be, hang on, let me just try and get rid of that. This point of intersection might be t lots of the direction vector from this one's first fixed point, line 1's called it, but it might be s lots of the direction vector in line 2. Okay, so we've got to allow for that. So in any problem where we're looking at the interaction or between two lines, you must specify them with different parameters here to allow for all possible cases. Okay, do you get it? So there we have it. Two lines in a problem implies t and s, not the same parameter there, because you're locking them down too much in similarity and making them have a common property that they don't actually have. So then our line 3, oh, that's unfortunate, it's given in Cartesian form. That's going to make us work hard. So remember, what we're trying to do is classify what the lines are doing with each other. Are they parallel? Let's have a look, show that they're parallel. So the first one, line 1 has a direction vector. What is it? 2, neg 2, 4. Direction vector is the coefficients of the parameter here. So you could call that 2 lots of 1, neg 1, 2, taking out the common factor there. Line 2 has a direction vector neg1, 1 and neg2. Oh, we can see here that 1 is a scalar multiple of the other one. So both line 1 and line 2 are parallel to that, and so must be parallel to each other. I think I would prefer to say that line 1 is k lots of line 2, where k is what? What do you multiply line 2 by to get this one? It's neg 2, isn't it? Okay, so where k equals neg 2. So if you did that, I think that is better. That's the definition of parallelism. Well, this is okay. You say they both got this common vector here. That's okay. They're using the same notion. But this idea of saying that one is a scalar multiple of the other, that where k equals neg 2, I like that a bit more. All right, so here let's have a look at, show that they intersect and find the angle between them. So let's have a look at these two, line 2 and line 3. Well, line 3 is like this. Okay, so we've got to see where they got that from. It was from the Cartesian form x take 1 on 2, using that. That's not true, and so on. So what have they actually done here? Substituting line 2's equation to line 3's. Okay, and leaving it in this Cartesian form. So we're saying now, we have to come up and just have a look at the equations here again. So line 2 is that one. It's going to intersect this one when the x's are equal, the y's and the z's are equal. Okay, so the idea therefore is that you're going to sub 1 take t in here in line 3, and t in line 3, and 3 take 2t in place of z in line 3, and try to find a t value. So we'll take two at a time. Take these two and try to solve them, and then these two and try to solve them, and we get a common t. So it's a common solution. Okay, therefore the lines intersect when you've got a set value of the parameter, you've locked a line down and you have a specific point, so sub it back into either of the original equations. The easiest one is sub it back into line 2. Oops, that's we look at line 2's upstairs here, sorry, up here. Sub it back into line 2. That t value is getting a bit of a mess up there now, and find the actual point. Okay, so remember, two lines intersect when equate the x's, the y's and the z's, no matter what form you have. So we've mixed it up here. I was going to simplify the parametric form, the Cartesian form into parametric form and put the x, y's and z's equal. You could do that, or substitute the x, y and z from one into either form or the other, and that's into, in this case, the Cartesian form. All right, so what we've got here is a little picture of what's going on for the second part of that, which is finding the angle between them. So here we have our intersecting lines, intersecting at a point, and we're saying line 2 has got that direction vector, and line 3. Now, how do they get line 3 here? Well, taking its Cartesian form, can you see these are the coefficients of the direction vector? There's only one thing wrong with that. See this here? Neg y take 1. So we really need to put that as y plus 1, and then these work. Okay, so notice that little problem there with neg y take 1. It's got to be y take. And so multiplying top and bottom by neg 1, we've got these are the actual components of the direction vector. And that's all we need. We don't need any more to find the angle between two lines. We just need their direction vectors. So just watch that, getting it from the Cartesian form making sure it's y-take, thinking back about the structure of vector equations and how they give Cartesian and parametric equations. Okay, so now we've got these two. The angle between them is going to be given by the dot product L2 dot L3 over length of that. And see here we've got just the size of it, so we're trying to find the acute angle. Doesn't matter which one we do there, but we're finding the acute angle by making it a positive cosine value here, and that will give us the acute angle, which is about 10.89 degrees. Okay, well, here it is customary to say 10.9 to 3 significant figures rather than 2 decimal places. Just depends on what the question asks for. Okay, now let's do the last one now, where we're asking to see if line 1 and line 3, what relationship they've got. Now, do they intersect line 1 and line 3? Let's just go back up and check the question, show that line 1 and line 3 are skew. Okay, so let's have a look. Line 1 and line 3. So here's the x of line 1, the y and the z, popping it into line 2's Cartesian equations. Then we can find, taking these two, we're on line 1, so the s value to make those equal is to be 1, and line 2 has to be 3 over 2. Now that's inconsistent. They put absurd. You can also put inconsistent. Okay, so you cannot have 1 and 3 over 2 simultaneously, because it has to be a point, a common point, doesn't it? And a common point has to specify a unique x, y and z. So the z being equal to the y on, sorry, the two z's being equal on a line or whatever requires a different s, if you like, from the x's and the y's being equal between the two lines. So that's inconsistent. We should check also, though, because we're saying they're skew, we should have checked, were they parallel? We've said they don't intersect. That's what we've said here. They cannot meet and are not parallel. We didn't actually show they're not parallel and therefore are skew. Okay, so we really should show, using the direction vector of each line there, we should show they are not parallel. And we could go on and find the angle between them using the direction vector. Let's just go up and check there that the two aren't. Show that line 1 and 3 are skew. It doesn't take much here. It's a big mess here, so we'll just get rid of some of this now and see if we can just do it. So here we go. The direction vector of this first line is 2, neg 2 and 4, which is 2 lots of 1, neg 1, 2. And the direction of this line, just remembering, it's 2, neg 1, because this is really over 1, but remember the neg y, we want y take, so it's neg 1 and 3. So we can say, considering those direction vectors, line 1 is not k times line 3. Or the direction vector of line 1 is not, therefore they're not parallel. So we should actually check that, because we're doing skewness by default, aren't we? We're saying they're skew if we can't show they intersect or are parallel. Okay, now, and you could find the angle using those direction vectors I just gave you. So if you dotted them, the cos of the angle would be the dot product over the two lengths. Okay, that idea. All right, so I get you to practice some of that now. So come down and see what you can do. Okay, so here's question 14. Going through them, just remember, if you want to show a parallel, intersecting or skew, you can only show skewness by this one not being true and this one not being true. So you've got to check, are they parallel to a system a system of elimination, basically. If they're not parallel, you can't find a consistent parameter for intersecting, then they must be skewed. Right, just remembering here that if you're looking at this one compared to this one, well, if you introduce a parameter here, you must use S, don't repeat T. Okay, so just keep that in mind for all of them. So that, see what they've done down here? They've used S for this line and T for this. You can't use the same parameter for reasons I said before. Fair bit of work there, it's worth doing all of them. So pause the presentation, have a go. Let's go down now and have a look at the answers. Okay, so there's 14A. Go to B. C and D. Last part of D there. Go to E. There's E. And F. All right, we've got one little bit to do, and that finishes up for lines in space. So come down, let's have a look. Now, the shortest distance between two skew lines. Now, you might be interested in doing this if planes were flying, not planes in space, but actual aeroplanes. You might be interested in the shortest distance as they fly through, and one is skewed to the other. But how close do they come? Maybe. All right, so here what we're going to do is take this from Hayes and Harris. I'll give a slightly different spin on it. Suppose line 1 contains point A, has direction vector U, and that's this direction down here. And line 2 contains point B, has direction vector V. Okay, so there we have it. So the idea is to translate line 2 so that it's down here, bring it down, so line 2 and 2 dash and line 1 intersect there. Okay, so we're looking at this situation here. Now, U cross V, there we have it, is a vector perpendicular to both U and V, and line 2 is parallel to the shaded plane containing lines 1 and line 2. Yep, so that's the idea of just bringing this down, translating it straight down, so it's parallel. So the shortest distance is the length of the projection vector of AB on U cross V. Now that takes a little bit of understanding. So what we're going to say here is, if you considered this vector from any point A to B and you stood it up, let's think about standing that up. Okay, and you want, here it's like that, you want the perpendicular distance. So if you stand it up, you're looking at the projection of that in the perpendicular direction, U cross V. Okay, so what is the projection? Let's go from, this could be any point, of course, because depending upon where it is, doesn't make any difference here. We want the projection of that in that direction. So what is that? The projection of AB onto U cross V. It's AB dot U cross V divided by the length of U cross V. Okay, so that's the idea here, that you're of this diagram. You're effectively saying that the length of the vector produced from any point on that first line, any point A, do it across to U cross V, and stand it up, U cross V, or the base of U cross V is point B on the other line. And what you're interested in this is in this, where you're standing up for the perpendicular vector. Okay, so that's trying to get some picture for you of why this works. This is actually the projection vector of AB in the perpendicular way. So it can be any point A, and it will differ there only in as much as when you have that vector, the projection is going to handle those differences for you. Okay, so it can be any point A, and its projection in U cross V. Okay, so this is going to vary, and so is this, therefore. But our ratio is going to be the same there at the end. All right, do you get the idea? You think about it so you don't have to memorize all these formulae. The idea of a projection, this diagram over here. Get any length, project it up into the perpendicular situation. So it's a projection of AB onto U cross V, which is AB dot U cross V divided by the length of U cross V. Okay, building a little bit there. Okay, come down, let's have a look at doing an example. So find the shortest distance between these skew lines. Notice one is specified with T and one is specified with S. Okay, so line 1 contains what? 0, 1, 2. So what we usually do if we want any point on the line, just substitute in T as 0. Okay, substitute T as 0, and so that's just the first point on the line, if you like, and has a direction. Now let's see, this has got a direction 1, neg 1 and 1. Line 2, can we take a point B on line 2? So what are we going to take? Put in T as 0 again in line 2 and start there, which would be 3, neg 1 and 4. And it's got a direction vector of neg 1, 2 and neg 1. I hope you're getting familiar with these different numbers, the constant and the coefficient of the parameter there, giving a point on the line and a direction vector. So we need the vector AB, so we'll go from A to B, 3 take 0, neg 1 take 1, 4 take 2, so there we have AB. We now need the cross product of U and V. So again, you probably would like to do it this way, 1, neg 1, 1, neg 1, 2, neg 1, and then do our cofactors, and we've got neg 1, cofactor matrices 2 by 2s there, neg 1, 0, 1. And so what is this D? So we want to project this vector in this one's direction. So it's AB dot U cross V over length of U cross V. So AB dotted, so this one dotted with this one gives us that one. Notice when we're doing that, AB dot U cross V can be done as a scalar triple product. You could have put AB up here. Where's AB? Trying to find AB. 3, neg 2, 2, because you're going to dot it with the vector product, and the vector product here would have been given by this. So this would be the scalar triple product, so you could have done that. Okay, and because it's a length, we'll put the length of that there. Okay, the length of the scalar triple product. Okay, so you might remember that. I think we had that back before. A dot B cross C. When you want to do a dot product with a vector product. A vector dotted with a vector product. Scalar triple product it's called, because it's a triple vector and it ends up a scalar because you're finally dotting the two vectors. Okay, so then we have the answer. Okay, time for you, and then you can have a rest. Fairly challenging presentation. Let's have a look at trying some problems now. So here's question 15. Find the shortest distance between those skew lines. Okay, so use that idea. I'll show you the answers now. There's 15. We'll just see if we can get B. 15A. And B there. And you're finished. Well, we've got a couple of other presentations to wrap this up. We want to look at planes in space now, flat surfaces, and see what we can do with those. But I'll catch you then. Cheers for now.